Dr. Davesh, I think it's the time now. We can start.
Yeah, we can start.
Okay. So, dear participants, let me introduce to you with the today's expert, Dr. Sumit Sood, who's a very good friend of mine and excellent personality, highly knowledgeable person. So, he did his master's from Thapa University, Patiala, in the field of design engineering, and then he moved to France for his PhD. From the University of Lille, he did his PhD, and after that he did his postdoctorate from University of Lorraine, France, and now he's associated with the Crystal Laboratory, which is one of the center of University of Lille. Uh, so he has an excellent publication. During one of the discussion, he told me he was working on one of the project on green hydrogen, where they are using bond graph and other optimization techniques. So today's lecture, he will be delivering on monograph-based modeling and diagnosis of complex multiphysics systems. So I hope that it will be great learning experience to all of you. Uh, so I would like to hand over the session to Dr. Sumit Sood. Thank you, Professor, for your time. And
Thank you.
I request you to please start with your presentation and lecture.
Uh, sh- sure. Thank you for your kind words. I just would like to share my screen. Okay. Let's see if my screen is visible to everyone.
Yes. I hope we woke you early in the morning today. I think it is
It's
about
okay.
seven there in the
Right
France.
now it's 7:35. Actually, I didn't also check, but at the time
Great,
the
great,
lecture was
great.
scheduled,
Yeah.
the laboratory doesn't open at that time, so I was not able to
Yeah,
access my
so
systems.
very good
So that's why
morning.
we had to.
It's very good morning to you with our, highly energetic
Sure.
and learned participants.
Yeah, sure.
Yeah. So
Okay,
over to you,
so
Professor.
let's. Thank you. So let's see if my presentation is visible to everyone.
Yes, it is visible.
Sometimes there are some kind of glitches. Okay, perfect.
It is visible.
So hello everyone. So today we are going to discuss about the one of the modeling techniques that we use here in University of Lille for developing the models for different complex multiphysics systems. So this will be the content that we'll be going through during this presentation. So first we will see that what these complex systems are, and then we will see that what is the motivation for modeling these systems and what are the use of that models that we have. And then we will see that how the bond graph approach that I'm going to introduce. Some of you might have heard about this technique or might not. So we will see together that what this bond graph technique is for modeling, and then we will see some examples of how to use this bond graph modeling approach, and particularly we will see that how we can use it for doing the modeling of complex system, and we will take the example of a proton exchange membrane electrolyzer, and then we will see a small demonstration of using specialized software for bond graph to do the simulations, that is 20sim. It is developed by a company in Netherlands. So we have the license for this, so I can share with you the simulation, and we will also see that how these models can be converted into MATLAB Simulink block diagram representation, and again what is the use of that, and then we will also see the other applications of these bond graph models and this approach. So we start with the definition for the complex multiphysics system. So any system that works in the combination of different physical domains such as electrical, mechanical, thermal, fluidic, or thermofluidic, or in the combination of these, that is called a multiphysics system or a complex system. Why complex? Because most of the time these models are highly non-linear, and there is a coupling between different processes which makes the modeling of these systems very difficult. For example, when we talk about the heat exchangers, if you see, it's quite a simple system to see, but when you think from the modeling perspective, so you see that there is a coupling between the fluidic and thermal domain, because the heat transfer also depends on the fluid flow. So that is just one example. And also there could be the multi-scale nature of these systems. What that means is that there could be some phenomena that are happening at the microscopic level, and then there are some phenomena that are happening at the macroscopic level. There could be some slow dynamics, there could be some fast dynamics, and to balance them, which one to ignore, which one to model. So that is also again a complexity in these systems. So just to give you some examples of these systems. So the combustion engine or IC engines, we all know this. So it is an example of a complex system in which you see that there are different physical phenomena are involved. So there is the mechanical part in which the pistons and other moving parts are they are doing their work in order to get the achieved result. And then there is also the thermodynamics of heat transfer of the heat that is produced, and also the fluid dynamics takes place in order to move the airflow mixture effectively to the combustion chambers, etc. Another example we can take is the nuclear reactor. So there are different components of the nuclear reactor. So there is a chemistry involved there of nuclear physics. There is also the heat transfer, fluid flow, and different sort of physical phenomena going on there. So again, there is a combination of these. Even our human body, if we take the example of human body, so there are different researchers who have also tried to develop a model for the human body. So again, it is the combination of different multiphysics systems. And the most common and most heard of these days, electric vehicles. So the battery system of electric vehicles again is a complex multiphysics system because it interacts under different physical domains such as thermal, electrochemical, and structural. Uh, so not only a single component can be of a multiphysics system, there could also be a combination of these multiphysics systems in order to get a desired objective to be achieved. For example, we see here the green hydrogen production system. So what happens is that the renewable energy from solar and wind is used either to directly charge the electric vehicles, or whenever there is a surplus. So it can be converted into hydrogen using the electrolyzer, and this hydrogen can then be stored and can be used for different purposes. It can be used for the fuel cell in order to generate the electricity again, or it can also be used to produce different uh, chemical fuels. For example, there was one work that I was part of was developing this SEDMIS process in which the carbon dioxide from industry can be reduced into dimethyl ether through this process that is called sorption enhanced dimethyl ether synthesis. So in this also the hydrogen from renewable energy is used, and each of this complex multiphysics system when combined together creates the another level of complexity. So today we are going to discuss about the model of the part electrolyzer. So just to brief you that what the electrolyzer is, and particularly what is the proton exchange membrane type electrolyzer is. So it is a device that is used to dissociate water into hydrogen and oxygen with the help of the current or electricity that is coming. It can be any source, but most of the time the one that we are concerned with is the renewable energy. So you can see here that the current is coming from the renewable energy source, in this case solar energy, and the water gets dissociated into hydrogen and oxygen. So there are two sides of this. One is the anode and the second is the cathode side, and there are the half reactions that takes place on the both sides. So on the anode side, the oxidation reaction takes place in which the hydrogen is produced and the proton ions are produced. And these protons are moved from this membrane, that's why it is called proton exchange membrane, to the cathode side, where it takes the electrons from the electricity and reduced through this reduction reaction into hydrogen. So this oxygen and this hydrogen are separate, so they can be collected and that can be used. So now it might sound like that it is something related to chemistry only, but that is not true. So if we take a deep look into this, so you can see here there are different uh, uh, phenomena that are going on here, and these phenomena are coupled to each other. For example, there is a source of electricity, so there is electrical domain, and then for the dissociation of the water into hydrogen and oxygen, for sure there is a chemical domain process that is happening, but also there is heat being generated there. So in that case, in order to effectively remove that heat or to regulate that heat, we have to deal with the thermal domain, and to flow the water effectively through these anode and cathode side, so we have to deal with the fluidic domain. And most of the time there is a coupling between these, which means that one phenomena depends on the another type of phenomena. So just to brief you that what are the different modeling techniques that we consider in our case is for the complex multivariate systems are either equation based, graphic model based, or miscellaneous models. So just briefly, let's see that what these models are. So the equation most models, again, there are two type of models. One can be static models and the second can be dynamic models. I hope that everyone is familiar with two type of different models, static and dynamic. So static are the one that doesn't evolve with time. In the dynamics, the parameters or the variables, they evolve with time. So in equation based models, usually the models are analytical models that are based on the technical know-how or the theory on the phenomena. So it is basically based on the physics. The semi-empirical models are the combination of analytical models and the experimental data. And the empirical models are the models that are developed through the experimental data in order to, for example, to find the relation based on the statistics. Then there are the another type that is called the graphical models. In this, the models that are developed, you can see them in the form of a graph or in a form of image. So they are very easy to interpret. So there are different techniques that are used. So some of them are, for example, the block diagram representation in MATLAB Simulink. There is electrical equivalent circuit diagrams, energetic macroscopic representations. This one is used a lot for EV systems, for electric vehicle systems. And then the one that we are going to discuss, the bond graph approach. And then there could be also the miscellaneous models that are used for specifically discussing or for analyzing some particular phenomena. For example, computational fluid dynamics, RSCAD, or if you have a lot of data about the system, you can go for the neural network models. These are also called as the data-driven models. So the first question comes in our mind is that what is the motivation for us for this complex system modeling? Why we want to model these systems? So the basic idea behind doing the modeling of this complex system is to develop a supervision platform or supervision system that can help us in achieving different objectives. For example, it can be used to analyze the performance of the system. So we can have a digital twin, for example, of the system, and then we can try to analyze the performance under different operating conditions. It can also be used to improve the design of that system. It can also be used to develop the control for the complex system. And for example, if the system is already working and we want to know, or we want to have a system in place that can detect if there is a fault in that system and it can isolate that fault. So for that, we can also use these modeling techniques. And also we can use it for prognosis, which means that we can try to estimate the remaining useful life of the system. For example, in your batteries, for example, for your phone battery also. So there are different algorithms that are working behind in the background that gives you the estimation of your remaining useful life of your battery. So, but what are the challenges that we have to face because of this complexity of these multiphysics systems? So, like I mentioned earlier, there is a coupling between these different physical phenomena. So that makes this system very difficult to model. And we actually wanted a tool that can be used for different uh, uses. For example, for developing the control, for doing the diagnosis, for doing the prognosis, or for the performance simulation. And we want a structured approach so that you can have certain steps that you have to follow in order to get the final model. And we need a kind of a tool that can be a unified tool. So it can be a single tool that can be able to model different type of physical domains. And it should be generic enough so that it can be used in repetition. For example, if we draw a model once, so it can be used for other parts also. So for this, the task for achieving this task, the skills that we require is the multidisciplinary knowledge of all these different phenomena. So before going further, so let's take a look in a simple examples of different uh, uh, physical domains. So if you see here, the first one is the example for the electric domain, in which you can see there is a resistor, there is a capacitor, and there is a voltage source, and this is connected to the ground. The second one is the example of a fluidic domain, so in which there is a pump, and then there is a valve that is used to fill a cylinder. The third one is a example from a thermal domain, in which there is a block that is being provided heat from outside, and this block is retaining certain heat and it is also releasing certain heat. Then there is a spring mass damper system. The fourth one, it comes from the mechanical domain. And again, then there is another example from the electric and mechanical domain. But what we want to see here is that we want to find some kind of an analogy in order to see that if these models can be compared with each other or not. So if you will see here that for each type of energy domain, there are certain elements that performs the same function. For example, the resistor here, it dissipates the energy in the form of heat. Here, the energy is dissipated because of the this valve. Here, if you see that there is also the energy side, the block, that is because of the thermal resistance. Here, there is also dissipation of energy due to the dampening effect. See here the capacitor, what the capacitor in the store, basically it is storing the energy. If we consider the thermal capacity of this block, so it is going to store the heat energy in certain form. And if you see here that this spring and mass, it is also going to store energy. And likewise for other systems also, we can see that the different systems, they can be segregated into different physical phenomena that are analogous to different domains. For example, the resistive phenomena, that means that it can reject the heat or dissipate the energy. Inertia phenomena, that can store the energy in the form of inertia. There could be a capacitive phenomena in which the energy can be stored in the form of potential energy. And then there could also be a source of energy. For example, in the first case, the source of energy is the source of voltage. Here, in the second, the source of energy is this pump. Then there could be a heat source. And here in spring mass damper system, the source of energy could be a force that is applied in order to excite the system. So with this thing in mind, so let's start the introduction to the bond graph approach. So what a bond graph approach is? So bond graph is basically a unified modeling tool based on the graphical modeling that is used to develop the model for these multiphysics systems. And these models are based on the power interaction between, or power exchange between, different elements of the system. So we will see that in a minute that what this means. But what is the benefit of using bond graph-based modeling for these systems is that a single model, first of all, it has a systematic approach. So there are 4 different level of modeling. So we will see how the bond graph satisfy all these 4 types of levels of modeling. And the same model, it can be also used for multiple purposes. So if we develop a model once, so it can be used for performance analysis, for doing the simulations. It can be used for developing the control. It can also be used for performing the diagnosis. It can also be used for doing the prognosis. So a single model can be used for multiple purposes, and that is what motivates us to use the bond graph. So if we talk about the 4 different level of modelings, the first one is the technological level, in which the system is seen on the macroscopic level. So we just want to see the architecture of the whole model. So in this, we see that what are the different components of the model, or what are the subsystems of the model. And it gives us the overall idea that how the system is going to work. And in case of bond graphs, we have something called the word bond graph that we will see that satisfies this technological level. The second one is the physical level, in which what we do is that we use different elements, like I showed in the energy analogy, that there are some handful elements that can be used to represent different phenomena, such as the dissipative phenomena, inertial storage, capacitive storage, or source of energy. So using these elements, we can define the different working phenomena or physical phenomena of the system. And this level is called as the physical level. The third level is the mathematical level. So we will see that the model that we develop here, although it is graphical, but it is can be systematically converted into mathematical equations that are most of the time are algebraic and differential equations. And the best part here is that we do not have to do this by hand. Although when this bond graph technique was developed, it was developed in the time when there was no good computational power in hand. So the people have used to do all the calculations by hand. So this is quite calculation friendly. But now using the structured approach in the softwares, we can directly generate these equations. I will show you this through the demonstration. And the next is the algorithmic level in which these mathematical equations are to be used to do the simulation. So we have something called as the causality here, in which that helps us to identify that what is the cause and what is its effect in order to see in which direction we have to do this simulations. So as I mentioned in bond graph, we have something called a word bond graph that is at the technological level. Then we have a bond graph, the model itself, that is called the physical level, and then the two other models that we have discussed, the mathematical and econometrical level. I will not explain it here. So let's first see that what a bond graph model looks like. So this is just a typical bond graph model of a PEM water electrolysis cell, the phenomena or the system that I showed you earlier. So at this moment, if you see it, you are not able to maybe you may not be able to understand what is happening here, but just I want you to focus on certain things. Just focus on the definition of the bond graph. So what I told you that in this it is the graphical representation. So you can see here that it's a graphical representation, and what happens is that the power exchange between different elements, it is representing through a bond. You can see here these arrows. So these arrows are called as the bond. So this represent the power exchange between the different components and different elements. So from this, the name comes the bond graph. So by the end of this presentation, I hope you all will be able to understand that what this model is. So just a brief about the history of the bond graph modeling. So it's quite boring, so we will not go in details. So it was founded by Henry Painter at MSD Boston in 1961 in USA. And since then, it has been improved by a lot of people such as Carnot, Rosenberg, Rishin Thoma, even my PhD supervisor, Professor Belkacem Oldboamama, is also one of the big contributors in this developing this bond graph approach. So it has been introduced at different universities in France, in Europe, usually in Netherlands and France. And here in University of Lille, we use this tool. And there are different companies in Europe that use these tools for the modeling. For example, you might have heard this PSA. This was a car company, but it has been closed. The Renault, everyone know this company, so they use bond graph approach. Then there are different electricity companies or nuclear companies that use this bond graph approach. And then there are aerospace companies such as Airbus, even NASA also use bond graph approach. So this is a quite powerful tool that is being used by different industry people also, and also in the academia. If we talk about India, in India also there are different institutes where this tool is being used. For example, in IIT Kharagpur, there is Professor Samant Rai, who is a well-known scholar in the bond graph approach. There is a professor in IIT Roorkee, in Thapar University also. These tools are being used. So just let's start with the definition. So what here we want to see is that how the power between the two elements is exchanged. So if we see here, we take a simple example to understand the definition. So there is a motor and there is a load. So what happens is that when this motor rotates, so from this point, if you see that the energy or the power is transferred into this rotational load. So to represent this, this power exchange between this load and this motor, we can represent it with this bond, and this bond represents the power. And for this bond, we have two associated variables that are called as the power variables. The one is E, it is called effort, and the F, it is called flow. And for the two bond graph, the product of this effort and flow is always power. Okay, for example, here you can see that for the mechanical power here, so it is the energy that is, or the power that is being exchanged between the motor and this load. It can be a mechanical power, so it can be represented by effort, that is your torque, and omega, that is your flow. So the power representation, like I told you, that this is the bond, this is called bond, that is used to represent the power exchange. And the arrow, this half arrow, this represents the direction of the transfer of power. So for example, if there's a system on the left side and then there's a system on the right side, so this arrow represents that the power is being transferred from the system A to system B. Then there are also another type of bonds that we use here, that is with the full arrow. In this case, they are just the signal bonds, and they are used to represent the signal processing in order to represent the sensors. For example, in this case, it could be the effort sensor or detector of effort. So in this case, there will be no flow, so only there will be the effort, and this will represent the sensor that is used for measuring the effort, such as pressure, voltage, temperature. And then there could be another sensor, that is the detector of flow, in which the effort will be 0 and the flow will be measured. For example, current, hydraulic flow, etc. Okay, so like I said, that each power bond, it has different power variables. So what are the power variables? So these are the variables that represent the power transfer. And like I said, that the product of these two is always power in case of the true bond graph. We will see that what the true and what is the pseudo bond graph is. But for example, the effort variables, they are such chosen that they are the intensive properties of the system. For example, for the thermal domain, we can see the temperature as the intensive property, or for the fluidic, it could be pressure. For electrical, it could be voltage. And the flow variables are the derivatives of the extensive variables. For example, for thermal, it could be entropy flow. For fluidic domain, it is volume flow, and for electric, it is current. So if I just represent quickly the efforts and flow for different domains, so you can see here that for different domains that we have certain efforts. So all these are based on the intensive properties, and this flow, they are the derivatives of the extensive variable or extensive property. And always remember that the multiple of these two is always gives you power. And this is when we call that the bond graph is the true bond graph. But when we talk about the complex systems, this might not always be true, because we want to represent certain phenomena in the system in which the product of the effect and flow, effort and flow, might not be equal to power, but still it follows the structure of the bond graph approach, and it makes it convenient for us to draw. For example, here if you see for the hydraulic, we can also consider the effort as pressure, and but instead of using the volume flow, we can use the mass flow, but the multiple of this two will not give you the power. Likewise, for chemical also, we can use the molar flow and concentration for representing different kinetics. And for thermal, for conduction, we can use the temperature as the effort, and we can use the heat flow as the flow variable. For convection, we can use the temperature specific enthalpy as a effort, and enthalpy flow as a flow. So in this case, when we talk about the thermal, when we talk about the conduction, it basically means the heat transfer between the between the fluid and the wall of the container most of the time in process engineering. And when we talk about the convection, so in convection, we are more concerned with the heat that is being transferred through the flow of the liquid or the fluid. So there are some another energy variables also that we use in bond graph approach. So the one is called the momentum of impulse. It is the integral of the effort variable, and then there is also a general displacement, that is the integral of the flow. So these two helps us in order to get the characteristic equations of the actual elements. So we will not go into these details because this doesn't interest us more. So just to show you that what are the different energy variables for different domain. So you can see here, no need to remember these for the moment. But if you see here that for chemical and thermal domain, there is no impulse variable, no energy variable for impulse. Why is this so? Because here, if we see that by definition that for impulse, the impulse is the integral of the effort of the system, and in case of thermal domain we have seen that the effort is temperature. So the integral of temperature doesn't make any sense, it doesn't have any physical meaning, so there is no impulse in case of thermal domain. So just to take an example, for example, here you see a multiphysics system, and we want to see that how we can select that what are the different phenomena that are going on here. So just to see that how this works. So for example, we can see this part, this is the fuel cell. So it comes under the mechanical and electrochemical domain in general. Then this part in which this electricity is being used to drive this motor, this is under electrical domain. From this resistor, there might be some energy being lost in the form of heat, that comes under the thermal domain. Then the conversion of this electrical energy into mechanical power, that comes under the mechanical domain. And this might be used to run a model, a pump, in which the pump will be pumping the water to this container. So this comes under the hydraulic domain. Here, there might be some process that is going on where you are maybe adding the heat or you are removing the heat from the system. So it comes under the thermodynamic domain, and there's a coupling between the two. And then the last is also the economic domain. We will not talk about this. This is not technical, but the bond graph approach can also be used for economy. So we can see that what are the different components of a multiphysics system and how we can segregate that into different domains, physical domains, and then we can also try to pair them with each other, and we try to define the variables or power variables for these components or these systems. So based on the chart that I showed you earlier, so we can see that for the thermal domain, what will be the power variables, for electrical domain, what will be the power variables, etc., etc. So now let's go for the first part that I said, that the first level of the modeling is that the technical level in which we want to use the word bond graph in order to see that how the whole system is working. So for example, if we take an example of an electric motor here, so you see here there is a electrical part, there is a mechanical part, and there is a load that is on the shaft. So in this case, what we do is that we represent each part with these blocks that represent the overall bigger component of the or subcomponent of the system, and we try to identify that what is the power exchange between these two parts. For example, here the electrical part, this outputs you the current and voltage that is used to drive this motor in the mechanical part, and this mechanical part will impart this torque and your angular velocity to the load. So this gives you the overall idea, and this is called as the word bond graph that shows the different subcomponents and their interaction with each other. Let's take another example for the word bond graph. For example, for a power station, so you can identify that what are the different parts. So first one is the reservoir, then there is a pump, and then there is a power exchange between the reservoir and the pump. And here, if you see here that although generally we consider that the pump will be working in the hydraulic domain, but there could also be the interaction in thermal domain. So if, for example, there will be the losses in the pipe, there could be a motor and there could be a source of electricity that is running this motor to run this pump. Then there's a boiler that is being fed through this pipe. There could be a heater here that is heating this water inside the boiler, and then there is a turbine, and then there is a load. So just by looking at this word bond graph, you can actually able to understand or to see that what are the different components of or subcomponents of this system and what are the power interaction between these systems. So another example, we can also use the piping and instrumentation design to generate the word bound graph. So here, if you see that there is a piping and instrumentation diagram for the PEM electrolyzer or proton exchange membrane electrolyzer. So here, this stack, this is the heart of the electrolysis cell, and the other parts are called as the balance of plant, and they are here in order to ensure the proper functioning of this system. For example, there are circulation pumps that are used to provide the water to this system. Then there are the separators that are used to separate the gases that are being produced from the water being circulated. Then there could be the circulating systems, there could be the heat exchangers, etc. There could be the valves here in order to balance the water levels on the both sides. So based on this, we can draw a word bound graph, as you can see here. So you can identify that what are the different subcomponents here easily, and you can see that what are the power exchange between these components looks like. And again, sometimes the coupling between the two subcomponents in two different domains can be represented either by these two parallel lines, or they can also be represented by a single line with a circle in the middle, and the power variables for the two different domains are written above and below this line. So this is another way of representing the same thing. So now what about this physical phenomena? If you remember the analogy that I showed you, that there are different phenomena that takes place under the different domains. So if you see here that all these, they represent the inertial elements that store the energy. For example, here there is the inductor, here there is the mass of the shaft, here there is the valve, and there are also the capacitance elements that can be representing the different domains and their phenomena of storing the energy, potential energy. And there can also be the resistors that are using the dissipation of heat. And then there is also a different type of element that is called the gyrator and transform elements. So what they do is that they transform the power from one form to another form. So we will see them in details, just to show you that how we identify these different components. So there could also be the sources. So for example, there could be a source here, that is here, this is basically a sink where the heat is being rejected into. Here the source is for the current from coming from the fuel cell. Here the source could be the water flow, and here the source could be the heat in case of the thermodynamic system. So like I mentioned that there are different elements in each domain, and these elements can be represented through a handful of elements in the case of bond graph. So let's see first that what are the different elements. So these are the elements that you usually need in order to represent any physical system in terms of bond graph approach. So the first one is the passive elements. So these are the elements that do not generate any electricity, but so not any energy or power, but they store or they transform or dissipate the energy. So for example, in this case, the resistance, like I said that it is used to dissipate the energy. The C element or compliance element or capacitive element, this is used to store the energy. I, inertial element, again is to store the energy. We will see the difference between these two, that what is the difference between C and I, although they perform the same function, but there is a difference. Then there are active elements that are the active source of power. So there is SE that is represented as the source of effort, and then there is SF that is the source of flow. So in case of source of effort, for example, the voltage source, in this case the voltage is the effort, so the source will be called as source of effort. And source of flow, for example, the volume flow rate from the pump, so pump can be called as a source of flow. Then we have the junctions. These are called the multiport elements that are used to connect all these elements with each other, or different systems or subsystems to each other. So we will see that what these 0 and 1 means. And then there are the transformation elements that are used to transform the energy from one form or from one domain to another domain. So by definition, so the bond graph element, like I said, that there could be the passive elements that can receive power, and then either it can dissipate or it can store it in the form of potential energy or kinetic energy. So usually it is represented the same way, like here, this is the bond, power bond, that is representing that the power is being transformed, or power is being transferred from the system to the element. And this R is used to represent the resistance element. Here R is the type of the element and R1 is the name of the element. Likewise for the C or compliance element, we can represent like this, and for I we can represent like this. So to give you the example of the resistance element or resistive element, so you can see here that there are different elements in different domains. For example, in case of electrical domain, we have the resistors that dissipate the energy in the form of heat. And then we have in mechanical domain, there is a friction. Again, in the friction, there is a loss of energy or power. Then in case of the valve, so there is the losses that occurs that helps in changing the pressure. In case of thermal, we can consider it as the resistivity or thermal resistance of the system. So in that case, it defines that how much energy will be lost to the atmosphere outside. So by definition, by this R, this is the element that is used for modeling any physical phenomena that is representing the loss of power or loss of energy, and it can be characterized by this equation, that is the effort and flow relationship. And like I mentioned, that what is the representation, so it is represented by symbol R. Then when we talk about the capacitive element, so it could be a capacitor in case of electrical energy. In the hydraulic domain, it is the capacity of the tank. In mechanical, it could be the spring. In thermal, it could be the thermal capacity or the capacitance of the object to store the heat. For example, here you can see that if the heat Q1 enters the system, so some of the heat will be stored and some of the heat will be rejected to the atmosphere. So this capacity is called the capacity or thermal capacity of the system. So here, by definition, the C element is the element that stores energy, and it has the characteristic equation that is the relationship between the effort and the integration of flow. So this is the basic difference between the capacitive element and the inertial element, that for capacitive element, the relationship is between effort and the integration of flow. However, in case of I element, the relationship is between the flow and the integration of effort. So there are different inertial elements you can see. For example, in in electrical domain, it could be inductor. For hydraulic domain, it could be the impulsion of the pressure in the pipe. For example, in mechanical, it could be the momentum or moment of inertia being stored in the body itself. And for thermal domain, there is no inertial element, as I mentioned earlier, because there is no physical meaning for the impulse for the thermal domain. Then the transformation elements. So these are the elements that are used to transform the energy from or the power from one domain to the another domain. And we will see this based on the different examples. So for example, in case of the electrical domain, we have the electric transformers that transform this power from U1 I1 to U2 I2, and always we consider that there is no loss of energy or power in case of the transformers, and simply the power that is before transformation and after transformation, that is always equal. And if you will see here, there is a relationship between the effort 1 and effort 2 that is represented by this equation, and similarly there is a relationship between flow 1 and flow 2 that you can see here. Likewise, we can see other examples. For example, for the hydraulic cylinder, so this can also act as a transformer that converts the hydraulic energy or hydraulic power into the mechanical power, again represented with the help of the transformer. Or it could be a lever, so lever also act as a transformer in order to transform the power from like small effort to the bigger effort. Then comes the gyrator. This is also a type of transformation element, but the difference is that there is a cross relation between the effort and flow. For example, here if you see that there is a relation between E1 and F2, and there is a relation between E2 and F1 that you can see here on the right hand side in the equation. So this is the basic difference between transformer and gyrator, that in gyrator there is a cross reference or cross relation. In transformer there is a direct relation between efforts and flow. To see the example, so we can see the DC motor can be example of the gyrator. Again, there will be no loss of power and energy here. So the power before transformation and after transformation will be equal. But you can see the relation here, that here the torque, it is directly proportional to the current that is being fed to the motor, and the angular velocity is directly proportional to the voltage. Another example we can see is the loudspeaker. In this case also, you see that there is a cross relation between the effort and flow variables. So the voice of the coil, the sound that is coming from the loudspeaker, that is produced by the force that is directly proportional to the current. And the back EMF that is introduced in the coil, it is directly proportional to the velocity of the movement of this coil. Then there are another type is the source of effort and flow. So there could be, like I mentioned, there could be two type of sources. Either it could be source of flow or it could be source of effort. So if it is source of flow, it is represented by SF. It could be a constant or it could be a time varying uh, 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 equation or relation. Similarly, if it is the source of effort, it will be represented by SE. And just to give you some examples here, for example, the current generator for the applied velocity, it is the source of flow. And for the sources like that provides the voltage to the system, or gravity force, or the force applied, the pump, battery, these all act as the source of effort. So like I mentioned, that the source can be either either the constant value. For example, here the flow rate of the water is constant, but it could also be the modulated one. So in this case, it might be, for example, you want to control this flow rate based on the level of the water in the tank. So in that case, you can have a detector here that will use the some kind of control in order to control this source of flow. So in this case, we represent it as like modulated source of flow. So in this, it is the controlled one. Now let's come to the junctions. Like I said that we will discuss it later. So there are two type of junctions, 0 and 1. So these junctions basically represents the conservation of power. So there are multiple ports or multiple bonds or multiple power transformations that is happening here. So they all connect here at this 0 junction. When we use the 0 junction, it means that the effort in all these junctions is equal. So we can also call it as the common effort junction. So you can see here by definition that the E1, E2, E3 and E4, they are all equal. So if we see from the power conservation law, the power entering this junction and power leaving this junction should be equal. So from that we can, in this equation, we can get F1 plus F4 minus F3 minus F2 is equal to 0. So this is basically based on the power conservation law here. So this is just the example to see that how this 0 junction works. For example, if you see here at this point, the flow rate that is coming from behind is maybe V1, and here there are different uh, flow rates. So in this point, you see that the pressure will be the same. So this is the 0 junction we have to use. Here this 0 because the pressure is the same and the flow rates are the different. So again, power conservation law says that P1 here should be equal to P2, should be equal to P3, and the sum of V1 should be equal to, sorry, V1 should be equal to sum of V2 and V3 based on the power conservation law. Likewise, we can see it for the electrical circuit also. If you see here that at this point, if you see that the total current is I, but here the current is being distributed into I1 and I2. That means here at the source, here across the capacitor and across the resistor, the voltage should be same. So again, we have to use the 0 junction. Likewise for the mechanical domain. So here, if you see we have to use the zero junction at the connection of this spring and this sorry for this mass and for the tire here, because they too will move at the different velocities. Okay, so we say that the effort will be the same between the two, so we have to use the zero junction. We will come to one junction now, that to understand that what the one junction means. So one junction is basically the common flow junctions. What that means is that the flow in all these power bonds will be equal. So F1 will be equal to F2, will be equal to F3, and will be equal to F4. Or we can also call it as the effort sum junction based on the power conservation law, if you see. So if we sum up all the efforts, it should be equal to 0. And of course, we have to consider this power convention. So power entering can be considered as positive, and the power going out could be considered as negative, and so is the signs here. So again, to show you some examples of the one junction, so you can see here, for example, let's see the very common example here. For example, for the electrical domain, if you see here that the current passing through all these three components, it will be equal. But in this case, the voltage drop across these elements will be different. So here we can see that the source of effort is E, that is the applied voltage. And for all the other elements, for the R, L, or C element, so all these elements, the current will be the same. So you can see here the current is the same, but the voltage drop will be different. So here we have to represent it with the help of one junction. For this mass, there is a force that is being applied. There is the moment of inertia here, I, and here there is also a friction. For all these three, the velocity component will be the same. So that's why we have to use a one junction here. Likewise, for the second part, so for the second mass, we have to again consider the one junction. And in between, because there is a difference of the velocities, so we have to use a zero junction. So let's see that how we can develop the bond graph for these systems. So we start with the simple spring mass damper system. So in this case, like I mentioned, that you have to see that what are the different velocities. So if you see here, there are two masses. So the two masses can move with the different velocities. So we will mark them with one junctions, and then the parts that are having the same velocity, so we can connect them like this. So you can see here there is a source of effort that is acting at this one, and then this is connected to this moment of inertia I ma, and then this is also connected to this losses due to friction. Likewise, for the second part, we can do that it is the inertia and the resistance due to friction. And now, in order to represent the difference between these two velocities, we have to use the zero junction here. So if we put a zero junction here, so from this zero junction, we can connect this spring C element, and this gives us the bond graph for this system. If we also consider the damper here, so in this case, what we have to do is that we have to consider that these two parts will move with same velocity, this spring and this damper. So in that case, we have to use again a one junction here to represent the interaction between these two. So we can also consider a thermal model example here. So there is a source of heat, that QS, that is heating this block, and then there is an ambient temperature TA, to which the heat is being rejected to. So in this case, we can represent this with the help of a zero junction here, because here the source of heat and the temperature at which it is receiving the heat, here capacity, it will be the same, and this resistance or this loss, this will be based on the difference of the temperature or difference of the effort. That's why we have taken one junction here on which we have connected this RA. So if you see here, this is also equivalent to this the electrical circuit. So in this case, this source of flow, it is basically the heat, and this resistance is basically the thermal resistance, and this capacitance is basically the thermal capacity of this block. And this ground here, where the
voltage is grounded to. So here that is the source of effort here for temperature TA. Okay, so once we have this model sorted out, the second thing is the causality. Like I mentioned earlier, that the causality is basically the sense that gives us the information about the effect and cause. So it helps us to identify in the bond graph model that what is the thing that is causing certain effect and what is the effect of this that will be seen in the system. So we have cause, that is causing something, and then the effect, that is the output. So in this case, for example, if we take two systems A and B, and then there is a power being transferred from A to B, and if we mark this line here, this is called as the stroke or causal stroke here. So this represents that A is imparting the effect on B. In turn, it will receive the flow. So in this case, the E or effort is considered as the cause, and the flow is considered as the effect. It could be the other way here. For example, here if you see, if the causal stroke is on the other side, so in this case, the flow is being imparted by body A on body B, and in this case, the effect will be seen as the effort. So we have different conventions for different components that we discussed in the beginning. So for source of effort, the causal stroke is always on the arrow side of the power bond. In this case, because it is going to give the effort to the system. And in case of source of flow, it is on the left side because it is going to give the flow to the system. For R element, there is not a problem causality. It can be in both ways. In in R element, either you can have it on the right side or you can have it on the left side. But what is the difference? Again, it is the cause and effect. In this case, if the causal stroke is on the right side, so in this case, the effort is the cause and the flow will be the effect. In case if you put it on the left hand side, so the flow will be the cause and the effort will be the effect. So in this case, basically it tells us that what is the cause and what is going to be the effect, and this helps us in solving the bond graph in order to do the computation. Then for the C junction and for the I junction, for the C element and the I element, in this case, we have something called as the integral causality, and there is something called as the derivative causality. So for the C, for the integral causality, we have the stroke on the right side, sorry, on the left side, on the tail. And in this case, if you see here that the flow is the cause and effort is the effect. And in this case, if you see the relation between effort and flow, so effort is equal to the integral of flow in this case. And in case of I, if we consider this kind of causality, in this case again it is called as the integral causality because flow is equal to the, or is a function of the integral of the effort. In this case, as it is mentioned here that we consider that, or we prefer the integral causality for the modeling for the simulation purpose, because in this case, when we will simulate the model, this integration or this integrator will help us to accumulate the energy, and it will also, we will be able to see the effect in the long term. So we have the information of the history of the evolution of the system. So in this case, the integral causality is preferred. The derivative causality, we will see that derivative causality is preferred for the diagnosis, in which we will be able to see the rate of change of one power variable, and the second variable depends on the rate of change. So in this case, we will see that derivative causality, how it is used for the diagnosis. But for the simulation point of view, we always consider that the I and C element should be in the integral causality. For the junctions, I will just go quickly through these. For the junctions, for one junction, there could already be one bond that will have the causality like this, which means that this is the source of flow, because in one junction the flow in all the system, all the power bonds should be equal. So there could be only one bond that is giving the flow, and this bond is called as the strong bond, and the others should be with this kind of causal stroke that is giving the effort into the junction. In case of zero junction, there could be only one source of effort, because the effort will be equal in all the junctions, and the all others should be in this causality. There is no exception for this. It should be in this in order to get the causal bond graph. For transformer functions, there could be two different type of causality depending upon that what are the variables that are known to us. So if E2 and F1 are known, so we have the causality like this. And in case of E1 and F2 are known, so we have the causality like this. But we do not have to be more concerned with this for in case we use the softwares to develop these models, because this causality is imparted directly by the software. So the software assesses your bond graph model and assigns the causality accordingly. So let's see that how this works. So now, for now, we have seen that how the bond graph model is developed. So we will see that how we can use it by a small demonstration, how we can model the system. So for example, if we consider this system, it's a spring mass damper system in which the spring and damper are connected parallelly to each other. In the absence of this force, we can see that these are the equation that governs the behavior of this system. And for example, if you want to model it with the help of bond graph, let's see how we can do that. So in this case, if we consider that there is a force acting here S, in this case, we know that this mass, this spring, and this damper, they all will move with the same amount of y because they are connected. And in this case, that means that their velocity will be the same. So in case of the velocity, it's a flow. So if the flow is same, so we have to use a one junction, and then we will connect all the elements to this one junction. So there is one element that is this F, this force, that is source of effort. Then there is this mass. So this is the I element. Then there is this spring with coefficient K. So this is here. And then there is a damper RC. So once we have done this, in this case, what we have to then do is that we can see first that what are the different efforts and flows in these bonds. And the first thing that we have to do is that we have to impart the causality here. So to impart the causality, so we have to first start with always with the source. So in this case, the source of flow, we need to have the like this. In this case, sorry, it's not a source of effort. This is sorry, this is not source of flow, but source of effort. So we have to have this power stroke here. For I, this is the preferred causality. For C, this is the preferred causality. And for R, we can put the causality either on the bottom or on the top. But because there is a one junction here and we have already identified the strong bond, so the junction has to be here. This causality stroke has to be here. And now we will quickly also see that how this model can be converted into a block diagram representation for the MATLAB Simulink. So this one junction can be replaced by a summation in which we know that there are four bonds. So there will be the four signals that will be coming or going out of this. So we can represent them like this. So each this signal represents the flow, because here this is the effort equal effort junction or flow sum junction. Then we know that the source of flow is directly F, so we can put this signal here. For this mass, we can based on the characteristic equation, we can, because it is in the integral causality, so we can have an integrator here, and this is the coefficient for the integration. So this E2, that is equivalent to E1, that will be put here, and this effort will be integrated, and this will give you the F2, that is the flow for this. Now this F2 can be used to calculate the E3, because here if you see, the system will give the F3 to the compliance element or to the spring, and it will give you the force back. So in this case, we integrate this F2, or that is equal to F3, that will give you the E3. And once we have this, we can also consider for this RC. For in this RC, if you see the causality, so what we do is that we give this F4, and it will in turn will give us the force E4. So you see here that F2 and F4 are equal, so they goes to this damping, and then this will give you the E4. So by like this, so we can convert this bond graph element into the subsequent this bond graph element into the subsequent block diagram representation. So you can use either the specialized softwares to model this directly in the bond graph approach, or you can also use the MATLAB Simulink if you have, in order to simulate this system. So just to quickly see that how this can be simulated in different softwares, just a small demonstration. So let's to simulate this, we consider that the mass is of 1 kg, the damping coefficient is 0.05, the spring coefficient is 20, and the force is of 10 Newton. So just to quickly see, can you see my screen? Hello?
Hello, Dr. Sumit.
Yeah, can you see my screen?
Yes, yes,
The software? Okay.
Yes, yes.
So just I have just drawn this the same bond graph model for the spring mass damper system here. So you can see here there is a source of effort connected to one junction. There is 1 M, there is C and R, and you can see here that there is no causality here assigned. So in this case, in our case, we do not have to assign it by ourselves. So once we process the model, so it will be assigned automatically by the software itself. So this makes our work easy. And the best thing is that the equations for this system is not even required to be written, because they are generated directly algorithmically from this model itself. So we have not discussed that how we can do that manually, but if you will see here in this software, it's a 20sim software, and if you click show equations, so you can see here these are the equations that represent the dynamics of this system. So they are directly generated. So we need not to write them one by one by ourselves. So this makes our work easy. And in order to simulate the system, so you see here that these are the different values that we have seen for the different elements. So if we simulate the system, so you can see here that the system oscillates like this. So this should represent the displacement, and you see that the displacement goes on reducing because of the dampening effect, and in the end, because this is the system will eventually come to the rest. And the same thing we can also do with the help of the MATLAB Simulink, like I showed you. So you can see here, so the same model that is being developed in the MATLAB Simulink. So you can use this representation. So this is the summation block. This is the source of effort. This represents the integration of the I element. This represents the damper, and this represents the compliance element or the spring. So if we run this system in this case, so it should give us the same results. So let's see if we get the same displacement. So you can see here that it gives us the same effect. If we compare them side by side, here you can see that they both have the same kind of response, right? So like I mentioned that we will see for the complex models also, this is a quite simple example. But if we see for the complex systems, just to show you one. So if you see here, there is a complex system that is being that has been developed in the 20sim environment. So you can see here there are different parts. This is what we are going to discuss in the coming slides. So for each subcomponent, there could be the bond graph models inside. And for example, again, when we process this model, and if we go and we see these equations, so you can see here there are a lot of equations. You can see here they have how many equations are there, and they are also segregated based on the static equations and the dynamic equations that represent this. So you can imagine that if we are going to write all these equations by hand for the modeling purposes, in this case, it's going to take a lot of time, and the chances of errors are quite high. And for example, if you change something here in this model, so if it is it is based on the equation, so you have to go manually change all the equations. But here only you have to just have to compile the model, and it will give you the equations. So I hope this demonstration is clear to everyone. So we proceed further. So now we will start with like how we can use this approach, or whatever we have understood about the bond graph approach in modeling this proton exchange membrane electrolyzer. So again, to brief you about that how it works. So it basically dissociates the water into hydrogen and oxygen with the help of electricity, and this membrane is used to transfer the protons that are generated on the anode side to the cathode side. These are the half reactions. And just to show you that how what this proton exchange electrolysis cell look like, so this on the left hand side, this is the stack, and each stack has a number of these electrolysis cell that are stacked together. And this is the exploded view of the electrolysis stack. So inside there is a membrane that is called the Nepean membrane, and on this membrane there are the electrodes are printed on this membrane. And then there are certain other parts. For example, there are the diffusion layers here, or gas crossover layers, that facilitates the removal of the gases which are being produced, and also in order to provide the current on the both sides homogeneously. And then there are the flow plates in the end that facilitates the flow of the water to the reaction site, and in order to also move out the hydrogen or the gases being produced. So although it looks simple, so it's not that simple as is, but we will see that how we can still model it. So based on the piping and instrumentation design of the electrolyzer, like I mentioned earlier, so we can develop a word bond graph. So if you see here that there are different components, and this tag is called as the heart of the electrolyzer. So this is what we will be focusing on mostly. So if you will see inside here, this is what I showed you just before on the 20sim software. So you can see inside the stack also there could be a different sub models or sub components. So here you can see on the left hand side, we have segregated the model into 4 sub models that are based on the different physical domains. So first one is the electrothermal domain. Then the thermal submodel could be a fluidic submodel or electrochemical submodel. But on the right hand side, now you will be able to understand this better. This is what I showed you in the beginning, that what the bond graph looks like. So we will see that this is the exploded view of all the bond graph of all the submodels. So we will see them one by one. So this part, this is the electrical submodel, electrochemical submodel, electrothermal submodel, whatever you want to call it. But you can see here now this one junction, as we mentioned earlier, that this one junction means that the current through all these power bonds is equal, but this effort, that is the voltage, is different. And this is usually used to represent this equation of the cell voltage, that is based on the Nernst potential and Butler-Volmer equations that are from the chemistry. We don't need to go into the details, but you have to just see that here how the bond graph is used to represent. So here, this irreversible voltage, this is a voltage that is used to convert the water into hydrogen and oxygen. So that's why it is being transformed into the chemical domain using a transformer. And these voltages here, like E activation, E ohmic, and E activation cathode, these are basically the losses because of the different over voltages inside the cell. So this can be represented with the help of different R elements or resistance elements, because this is the loss. So we have represented this with the help of R element, these three. But in this case, in case of the electrolyzer, what happens is that this heat is not actually lost to the atmosphere, but it is actually utilized in order to increase the temperature of the water inside the cell. So in this case, we use a modified form of R element that is called as the RS element. So it is a two-port element that connects the electrical part to the thermal part. So whatever the energy is being lost here as the electrical energy is being converted into the thermal energy. and this thermal energy goes to the thermal model.